Okay. Great. Okay, hello everybody, and very welcome to the crash course for digital signal processing. Today is the first lecture. Mostly, today I'm going to define some new subjects, the new titles maybe. You will get familiar with some new titles, some applications of the digital signal processing, and you will be actually motivated for your future understandings and for your future effort, whether you want to choose this kind of this area as your interested area, or maybe you will forget it forever. So it depends on the first lecture. This lecture is going to motivate you for signal processing. So the course named Digital Signal Processing, but it's actually more than digital signal processing. As you could see from the schedule, which has already been uploaded. So we have almost 32 hours. I hope nobody has problem with English. So because I have problem with the talking German, I can understand somehow, but my speaking is not so well. So that's why I have to give the lecture in English. So if you just take a look at your glimpse on the schedule, you'll see that just the first 6 lectures are going to talk about the basic theories of the DSP, which these 6 lectures are actually covered in one complete course in many countries as a digital signal processing theory. So the first 6 lectures, are actually a completely crash course on the digital signal processing basic theories. These theories are applicable in all areas of signal processing, no matter of whether you're dealing with the image signal, video signal, speech signal, or any other things, and biomedical signals, whatever. So we try to cover the basic DSP theory in the first 6 lectures. So it means that this week, until the end of the week, we'll finish the DSP theory. So then afterwards, we'll go through some more applicable and more real stories that goes beyond the signal processing, which are actually dealing with random signals. It's less likely that you deal with deterministic signals. And DSP theory actually only cares about the deterministic signals, or at least the theories are developed based on the deterministic signals mostly. But then we go through this the statistical signal processing, or SSP, which is actually another course, but we try to crunch everything in just 2 lectures to just pay attention to the most important subjects that go through this statistical signal processing, or SSP. So the random signals and the properties of the random signals, whatever necessary for the course. And then we go through the filter banks and multi-resolution analysis, which is actually another course in a semester complete course. Then we'll talk about some mathematics in signal processing, or machine learning in signal processing. Some machine learning based algorithms which are really useful in many projects and in many real applications. And then we go through the multi-sensor signal processing. So we're just giving you some basic leads to different aspects and different areas which signal processing actually deals with. So we'll finally understand why such kind of outlines are selected for you. So the multi-sensor has another name called array processing. Frequently you will deal with, you'll see such kind of, these are the terms that you will deal with in real applications, array processing. It's actually multi-sensor processing. Then we deal with the blind source separation, which is actually multi-source processing. So when you say source separation, it means that the signal itself contains so many sources. And how you will deal with such kind of signals, which are not a single source. It's not just a source and a noise. It's multiple sources at the same time, together with the noise or any other corruptive effects. Then we have adaptive signal processing. It means that many of these theories that we explained so far until here, they are maybe just applicable in a batch processing and not in an adaptive case or in a real-time sense. So we talk about the adaptive signal processing, some basic ideas, and then we go through some clear signals. So we have two choices here, but all the theories that we have talked until here, until the 11th of April, would be applicable to all different aspects or all different signals that we have in the real scenarios. And we have just selected two signals, which are mostly taught in the courses in the universities, the speech signals and the images. So, and then we have the review over the course, and any questions that are maybe arisen by the students, we can just discuss about the ideas. We can discuss about some projects, maybe if you are interested to have some maybe collaborating on projects and then coming up with some ideas or papers or whatever, then we can discuss about that. And also the projects that you provided before the exam would have some extra points for your exam, and it's actually considerable extra point. So it means that if you get 2, then using the project, if you have the project done completely together with the report, then you will get 1. So these are the outlines which we are going to cover in the course. If you glimpse on the subjects, on the titles, you'll see that we have the theory, the basic theory. Then we have the signals which are random and not deterministic. So it means that the first part just deals with the deterministic signals. Then we deal with the random signals. Then we go through different representations of the signal. So not just going to the time domain, but we can go also through the time and frequency or time and scale, which are called filter banks or multi-resolution analysis, which also has another name called wavelets. So we have multiple domains at the same time. So these are called multi-resolution. Then we have some machine learning based algorithms. So it means that we try actually to have a learning in the process. So we try to learn from the signal itself, not doing everything unsupervised. And then if we have multiple sensors all gathering the same signal, would it have any extra point for us to have multiple sensors getting one signal? Yes, it has. And all the theories going beyond array processing is the thing that is an advantage or an extra point that you will get if you have multiple sensors gathering the same signal. Then if you have multiple signals integrated in just one, how you will separate those interested signals and then dealing with. That's the BSS theory, then going through the adaptive or real-time processing, and then we have 2 different types of signals. That's why the outline is actually lined up like this for you. There are some topics that just if you're interested, you'll see just in front, and they're not bolded like this. Just in case that you want to know what are the small subjects that we're going to cover in each of these outlines, you can just see here. like the machine learning, which is more prevalent in this university, you'll see that some basic algorithms like, SVD, singular value decomposition, PCA, LDA, k-means clustering, GMM, EM, and some basic optimization methods, convex optimization methods. And then localization for generalized cross correlation method, SRP methods. And we're doing beamforming, adaptive or fixed beamformings. We do ICA, and there are some branches of the ICA just recently developed, like IVA and canonical correlation analysis, or CCA, and sparse component analysis, SCA. And also we have learning-based source separation methods like NMF, non-negative matrix factorization. We go through very briefly to the neural networks and the new idea of deep neural networks. Specifically, we go through the sparse autoencoders and why they are useful actually, signal processing applications. And then the adaptive processing like LMS, RLS, and Kalman filter very briefly. And then we talk about the speech signals, how to extract the features from speech. The most prevalent features like the MFCC features, mel cepstral coefficients, mel frequency cepstral coefficients, MFCCs, and the delta features, dynamic features. And then some just briefly talking about how we do a speech enhancement. We just go through the first and the most simple algorithm of speech enhancement, which is actually spectral subtraction. We don't want to go through the details. That's one specific course. And then just briefly talking about the image, because in this university, hopefully, we have a broad, classes of image processing, computer vision, and so on. So we don't need actually to talk about images that much. But about the speech, I think there's no course here in the university as far as I know. There is no course talking about speech processing or speech applications, at least. There's just one seminar, and I think one of my friends is actually giving that seminar about the speech recognizer, but it doesn't talk about the speech. It's just how the recognizer, which is mostly the machine learning algorithms, and designing an acoustic model and some graphical things, which is actually language processing. It doesn't care about the speech itself as a signal. So the website for the course, probably you have already seen the website, so you can register in the website. I will upload the slides, exercises. I don't know whether we will have a tutorial for the course or not, in contrast with the previous semester, summer semester, that we had 2 tutorials. Unfortunately, at least by this moment, we don't have any tutorial. Probably I will just, I will upload the exercises, and then you will do it, and then scan it, or if you want to type it using the LaTeX, then you can do that, and then just send me through email. And finally, I will just write you an email that whether you have been qualified for the exam or not based on your homework solutions. And probably that's the way that we go through that. But I will upload the solutions, or at least I will write down by hand, and I'll scan it the same way that you've done. I will put some additional notes that definitely they are so useful. And we have the lectures and also my videos from the previous semester, summer semester. They're already in the YouTube, and they are already in the course website. You can just use it if you want to have a pre-knowledge about the next lecture, what's going to actually come up in the next lecture. There are significant differences from the previous semester, so for those who are attending for the re-exam, they're doing well, because if they're going to give the exam of this semester to be considered for the previous semester, summer semester, there are a lot of differences. If they don't participate, I don't know whether they can come up with good score in the final exam. Then we have some literatures, we have some books, several books. You can use any book that you like. I don't prefer anything. because I even by myself used different books. I just brought one of the samples, and this is one of the good books that I'm using, Digital Signal Processing, written by John Prokes, Northwestern University. So this is one of the best books that I normally use. But there are very good lectures, and the book from, you want to see it? From Alan Oppenheim, University of MIT. So he has very good lectures, both as a video and also the book. They are all gathered in his book. Very, very nice book, and I have actually, I started my DSP reading that book completely. So that's a very nice book. And it contains so many examples. So it's full of examples if you want to go through the examples and to be able to cope with the exam. That's, that should be one of your preferences. And the Prokes book is also coming with so many nice examples. Any announcement I will put in the website, so you will be announced by anything, any news, anything that can happen. And I will also put some sample problems, just the same way that I did it for the last semester. Even you can go through the last semester website and you can see some sample examples. And this is my email address. You can drop me an email if you have any questions, if you want to give me the solutions for the homeworks, if you want to talk to me about the projects, or you want to give me the reports, whatever, just you can catch me through this email, Gmail. For the solutions, you can arrange groups of 2 people. And I think if this is the number of the students participating, so there will be just one odd group, and if anybody prefers to have a group of single person, it doesn't mean the group. He can just say right now. Otherwise, we can make a group of. Yes.
I don't know if I do those projects because I already have the admission for the exam. Maybe I do them for myself, but I won't commit them.
I have so many ideas that are just on the verge of being published as a paper. So if you are interested, you can just take one part of that idea, implement it, and then we can make a paper. If you don't need the score for that project, at least you can have a paper out of it. So there are different ideas. You can go through a complete project which has already been done by some other student, some other university, reading through that and then re-implementing those stuff and having your own statements, making another report out of that. But I need to know that you have understood everything. There are many subjects that are already defined by so many other universities. You can find, just if you Google it, you can find so many reports together with the MATLAB examples and so on. But that's not what I want. What I want is actually, I need to know that you have understood everything. So the theoretical part should be explained actually completely in the report. I should understand that you know that what you're talking about. Then implementation stuff, having good curves which are representative of the idea and what you have understood, and then having good references and so on. You will get your score. But it's not just like to imitate whatever somebody else has done somewhere else and then just copy and paste it, something that some of the students did it for the last semester, even they didn't know that what they are doing. So you will not get a good score if you just imitate and mimic everything. So I need to know that you are understood, because it's not a new course. It's everything is already been done. So you can find new applications. As I said, I have so many new applications and so many new things to be done. If you want to participate in those new things, then I just say warm welcome. You can go through that, and if the result is positive, then we can get a good paper out of that. Thank you so much. It depends on yourself. So that's the final project, which has extra point. It doesn't mean that if you if you get the final score, if you get it completely, you don't need to do the project. It's just for yourself. The programming language, it should be MATLAB or C or Java, but we should actually coordinate beforehand. So the written exam would be on the 2nd of May in the afternoon. I prefer to be in the afternoon, but if you prefer to be in the morning, we can make it at 8 to 10 or 8:30 to 10:30. Depends on you. And it will be 2 hours. And I think we can directly delve into the theory. Okay. Any questions so far? Yes, please.
So should we form a team of 2, or is it going to be?
Yeah, I prefer to have a team of 2, but if if there is just a single person remain, then we can make it just one group as a team of 3. That's all. Okay. Just send me an email that we 2 are in a group, or you don't need actually. In the first homework, you will just make it in a group of 2 people. Okay. The main goal for DSP theory, we're actually talking about so many different categories, but they are actually related and associated with digital signal processing. Starting from filtering, different types of filters like linear prediction filter. Maybe many of these names are already, you've got familiar with those names. I just repeat it with my different words, with different statement. So linear prediction, autoregressive models, or AR modeling, or AR filtering actually. Infinite impulse response filters, or IIR filters. We have so many abbreviations in the course, so you'd better to get familiar with that. From now on, I will just talk about the abbreviations. I will not go through the complete phrase. So, IIR filters means infinite impulse response filters. FIR filters, or finite impulse response filters, and so on. We do analysis of the signal. As an example, we do the spectrum analysis. So we talk about the frequency representation of the signal and what goes through the spectrum, from the lower frequencies to the high frequencies. Then we have multi-resolution analysis, like the filter banks, wavelets, and so on. We'll talk about some compression. It's not specifically a lecture for a compression, because compression by itself has its own theories and it's as a course. But we just talk about some ideas that also are used in compression, like the PCA. Some lossy compressions like PCA. You know PCA, everybody knows PCA, I think. You don't know that? Okay, we'll go through that. Principal component analysis, or for the mathematicians, they say Karhunen-Loew transform. Or maybe the other way, but doesn't matter. It's just the same name. Or some people, they say Hotelling transform, because one of the guys that went through that is Hotelling, Mr. Hotelling, so it's Hotelling transform. Then the idea of JPEG compression. We have the concept of synthesis of the signal, linear prediction coefficients to synthesize a signal which is random and together with some conditions. Hidden Markov model, probably you have heard about that. HMMs, or hidden Markov model, is a famous model for both analysis and the synthesis of a signal, which is random. And we will talk about the states of the signal. Then we talk about the separation as a specific concept that can contain ICA, independent component analysis, independent vector analysis, non-negative matrix factorization, and so on and so forth. And we talk about some learnings like GMM, HMM, and so on. Or dictionary learning, for example. What are the concept of dictionary, which is very important. Sparse dictionaries, overcomplete dictionaries, undercomplete dictionaries. What are these concepts? And all these things are supposed to be applied to the digital signals. And what is a digital signal? What's the difference between the digital and maybe the analog as a contrast. Well, there are so many applications. Well, the number of applications is actually uncountable. You're not able to count the applications that are for the signal processing stuff. So it comes from the space applications, space imagery applications, and gathering the information, whatever, like the Mars radar. You know, everywhere you have signals, everywhere. It's not possible to find even a single entity in the world without having a signal. So if you just look at yourself, there are, you know, uncountable number of signals in the body. And for example, the source separation, blind source separation, it actually started with a biomedical signal. So people saw when I say the people, Christian Jutton and Harold, they were working on a biomedical application, and they saw that there is just one nerve passes through the knee to the brain, but it contains two signals at the same time. But that was, you know, posing this question for these curious people, that how it's possible there's one nerve that contains two signals at the same time, but the brain can easily understand both of the signals, the contents of these two signals. That was, you know, the kickoff of the blind source separation idea. So we have signals in the space applications, medical applications, ECG, EKG signals, whatever, brain signals or heart signals or many, many other signals. In commercial projects, we have the image, speech, sound, audio, so many other signals, the video, or the telephone applications. We have military applications like the radars, sonars for the submarines and so on. And tracking stuff, tracking the airplane, tracking some missile, tracking whatever. Industrial applications for the oil, minerals. You know, one of the greatest applications of source separation was in oil industry. They were using some explosions on the surface of the earth. This explosion passes through the layers of the earth, but it has some reflections. Different reflections mean different layers, but they can actually learn that to know, for example, this kind of reflection is associated for, you know, a kind of rigid layer, or this belongs to oil, something liquid, and so on. So there are many explorations in the oil industry that's just done by signal processing. And scientific cases for the earthquake, seismology, and data acquisition, spectral analysis, and many, many, many other things. So I hope that I could have motivated you for the signal processing. And then we start with two of the most famous and prevalent signals, which are audio and image. So initially, most of the signals are not digitized. They are just analog signals. They are coming out of nature. When they're coming out of nature, normally they are analog signals. Like the audio signal, there is an organ inside everybody's body, containing the human or any living creature, that produces this kind of audio signal. Which, for example, for the human case, we call it as a speech signal, or for the singers, it's audio signal. So these organs, they are actually collaborating to each other in order to create a kind of signal which is called speech or voice. But this is an analog signal which is propagated through the molecules interactions. And if you have a media here, for example, air media, then it passes through this media, through the wave propagation algorithms. And then it's actually recorded by a kind of device or sensor, which for the case of voice, we call it as microphone. So the microphone is actually triggered by the pressure changing, by the variation of the pressure of the air, and then it produces electrical signals out of that. So it just kind of transduces a wave pressure or a mechanical signal to another type of signal, which is electrical signal. And that signal is actually going through a device which is called analog to digital converter, or simply we say A to D. A to D is a device which digitizes the electrical signal, which is already analog, and then it gives it to the computer. When it's in a computer, every programmer can just take this signal. It's inside the memory of the computer, and it can deal with it and do any kind of processing that he needs. Any kind of processing. Enhancement, noise cancellation, reverberation cancellation, compression, whatever. And then the reverse process can take place. So it means that you have a digital signal. That digital signal is useless. It's useless for a human. So what they do is they use a reverse processing, which is the D2A converter. They try to make it as an analog signal, and then giving that to the speaker, loudspeaker, it again transduces the digital signal into the analog or the mechanical signal, which is actually the air pressure. And those variations in the air pressure, you can just hear it by your normal feature that you have in your body. And if the processing is, for example, for the case of cleaning the noise, then looking at the input and the output, you will understand that, okay, the noise is already cancelled. The quality of the signal in the output is much higher than the quality of the signal in the input. Or, for example, if the signal in the input is a mixture of 2 signals, 3 signals, 4 signals, whatever, and it's not understandable by a person, or at least it's something annoying, then doing the process, a kind of process, for example, which is source separation, then you will have 4 loudspeakers, each broadcasting or propagating a signal which depends on individual signals contained in the input. Then it's much easier to understand it. If you just play any of them individually, then you will see, okay, the first speaker said something like that, the second speaker said this, and so on. And for the case of the image, this is in the same way. The only difference is that, for example, for the acoustic signals or for the voice signals, that's a time signal, mechanical signal that's changed to the time signal, time domain. But for the image, it's just a space signal, X and Y. So you have pixels, X and Y. Inside the pixel, you will get the information containing the intensity and the color. And this is something done by this sensor. The sensor is called camera. You take the picture. Again, you have to give it to the A to D converter. Sometimes this A to D converter is already put inside this camera. And nowadays it's mostly here, inside the camera. So you get the data in your memory, put the memory inside a computer, try to process it. And you can just do in the process. Afterwards, you can just make it, shown, for example, by a video projector or by an LCD or LED or TV or whatever. So these are the processes. What you have is actually an analog signal, but it's, you cannot deal with analog signal inside the computer. The computer only understands bits or bytes. So zeros and ones, nothing more. So even the amplitude of the signal should be somehow encoded into bits. That's why if you have the analog signal, you need a kind of A to D, both cases. You will take samples of the analog signal, and then you have to deal with these samples, inside the computer as bytes or real numbers or whatever. Here is an example of ideal sampling, a natural sampling, and the flat top sampling, which we'll talk about these different types of sampling, or it's not different type, it's actually what you imagine that the sampling should do and what's actually done in an A2D. We will talk more explicitly on it in coming lectures, in the coming slides. Examples of speech signal in time domain and in multi-resolution domain is here. The left-hand side is actually a signal, a speech signal in time domain. So if you plot a signal using MATLAB, for example, for a wave signal, you'll see such a thing. These variations, for example, for someone who is already expertise of speech, you can easily understand that, for example, these places with high intensity should belong to voiced part of the signal, and those lower amplitudes might belong to the unvoiced part of the signal. And what are the voiced and unvoiced? These are phonemes that normally people talk. For example, A, O, E, these are voiced parts, which normally they trigger your vocal tracts. But the unvoiced parts are normally those parts which doesn't care about the vocal tract. They're mostly produced inside the mouth, using the tongue and the mouth and the environment inside, like s, sh. So, for the voiced parts, normally you have higher amplitudes. But even if it's not possible to understand that, you can go through the multi-resolution analysis of the speech signal. Here you see the time versus frequency. This is called spectrogram. Spectrogram is a graph which represents the signal in time and frequency at the same time. So a simultaneous representation of a signal in time and frequency at the same time. It's called spectrogram. And here, just associated to these high amplitude parts, you see, for example, this part here is represented by this kind of spectrum. And you see harmonics here, and these are the harmonics which are associated to the vocal tract fluctuations. Because everybody has vocal cords, and these vocal cords, they actually resonate with a specific frequency. That's called pitch frequency. Pitch frequency, which is unique. For everybody, the pitch frequency is unique. And it's one of the ways that they actually produce some kind of speech locks. So you have fingerprints, which is unique for everybody. We have also another thing which is unique for everybody, and that's the pitch frequency. Just depending on, the vocal cords fluctuations or the oscillations. So the first frequency is called the pitch, the first harmonic here. The first harmonic part is actually belonging to the pitch. But then you have other frequencies, and the harmonic of those frequencies which belong to the vocal tract. There's a pipe that the air pressure actually, when it goes outside the lung, it actually goes through that vocal tract. There's a pipe. And then it comes to the mouth. That pipe, because of the pressure of the air, it actually creates some resonance and some natural frequency resonances. And those frequencies which belong to those vocal cords, vocal tracts, they are actually called formants. And these formants, they actually show themselves as these harmonics in the signal in the voiced part of the signal. So for the voiced parts, you see these harmonics. That means these parts should belong to voiced phonemes, like A, O, E, and so on. The formants are different. The pitch frequency should be almost the same, unless you trigger something extra, like we call it Lombard effect when you shouting, for example, because of noise in the car. Normally you're not talking naturally. you're shouting, and that's called Lombard effect. It means that the pitch frequency actually changes. The same thing happens for singers. We have actually a normal, what do you call it, as in the music for the musicians, they have a normal what? Rhythm, yeah, maybe. No, it's not. There is a specific name for that. The octave or something like that. I know the normal octave, and then the higher octaves or the lower octaves, and so on. So the normal one is actually showing your pitch frequency in the normal case. But when you go to the, for example, a singer, when it goes actually to the higher octave, for example, we have do, re, mi, and so on. When he goes actually to the higher octave, the pitch frequency has a shifting, so that's called pitch shifting. And that's a Lombard effect. It normally happens when you are in the car with a lot of noise. So in a normal speaking, you have the pitch frequency which is almost constant, and then you have formant frequencies for voiced signals, but for the unvoiced parts, it's normally like a noise, a pseudo noise. It's called a pseudo noise. And noise is actually a kind of signal, random signal, which is actually spread over the spectrum widely without any reason. So you don't know actually what should be the value of intensity in this frequency or that frequency. So that's just wildly spread over the spectrum. But for the unvoiced, for the voiced, it's not like that. Voiced phonemes are more organized and more important. So that's just a simple example of a speech signal in time and frequency domain, and we have softwares for that. It's called there's a software, very nice software. It's called Prot, and I actually encourage you to download this software, which is free. Just search for this software, which is Prot. That's for speech analysis. You can download this software and you can use it, and I'll probably give one of the homeworks, at least one part of the homework, using this Prot software. It's very simple, very easy, but very representative and informative. You can get so many informations out of that. If you just feed an speech signal into the Prot software, then you can easily see the pitch frequencies, formants, the spectrogram, and many other information. And also the Cepstral MFCC features, whatever feature you need. Then we have the image signals. Image signals, they are in different domains. So they are actually in a space domain, it's not time domain. If you add the time as another entity to the image signal, then you have another type of signal which is called video or movie. So the video signal is actually the images which you have, for example, 30 images per second or 30 slides per second, then it's called the video signal. So you have another domain added. That's all. But it's actually originated based on the images. For the image we have X and Y, vertical and horizontal. And depending on how many bits you want to assign to the image, you will get different resolutions. You can have color, or you can just deal with the intensity in a grayscale from black to the white. When the intensity is the highest, for example, if you have 8 by 8 or 8 bits per pixel, with 8 bits you can go from 0 to 255. 255 is white and 0 is complete black. And whatever is in between these two numbers is just grayscale. And if you have 24 bits per pixel, then you can also add, for example, color and higher resolution also. So what is this funny 1 bit per pixel? it actually makes sense, even though that it's, you know, in the just first glimpse it looks crazy, but it's something that we have. 1 pixel camera. In 2008, in Signal Processing magazine, people from Rice University, they actually following the ideas and the theories of people in Stanford University about the compressive sensing. They actually developed a new idea, a new kind of camera. They called it as 1 pixel camera. And it was published in the Signal Processing magazine in 2008, I think April. And that was the 1 pixel camera that they actually devised. So 1 bit per pixel, maybe not 1 bit, but we have 1 pixel camera. So it's also a new theory. And we don't need actually to go through that. For any images, we can have different resolutions. For example, if we have a colorful image like that, we can also represent it based on the red, green, and blue. So we can have RGB, or we have different types of representations of image signals. And also, the same way that we talk about, for example, speech, here also we can have different pixels per, different bits per pixels, and we can get different types of quantizations or different resolutions. If you assign less bits per pixel, then you can have an image which is more blurred and not too much representative with the details. And if you assign, for example, 8 bits, you will get better. Even more, you will get better. But theoretically, it can be provable that adding more bits after a while actually is saturated and it doesn't make any difference for your eye. So, as far as I remember, if you have a camera with 6 megapixels, then more than that is actually not necessary for your eye. The only difference that it actually creates if you have more pixels is that if you want to zoom in or zoom out, that makes the difference. For example, 6 megapixel camera, if you just take a photo, doesn't make difference between 6, 7, or 8, or 10, or whatever. But if you try to zoom it in and make a poster out of that, then it makes a difference. So the limit is actually the boundary value is 6 megapixel for the eye. We have multispectral imaging, the one that's normally done in the satellites. Satellite imagery is really interesting area of image processing. So there are different types of cameras normally installed on satellites. We have multispectral cameras, we have panchromatic cameras, and we get so many informations out of that. One of the most famous types of cameras are called multispectral cameras, and they do multispectral imaging. They have specific wavelengths that the camera just takes that wavelength, whatever it can actually be recorded by the camera. So the wavelengths here are mentioned, for example, for the white, for the red, green, blue, and so on. But any of these wavelengths is actually associating with a type of signal. For example, when they, I don't know, maybe we can have, yeah. For example, the band 1, 2, and 3, if they are merged together, then that's the representation. If 4, 3, and 2 are merged together, you'll get such a thing. And if 7, 4, and 2 are merged together, you'll get such a thing. And any of these information will get you something, some idea about the green area, the water area, if there is water somewhere, or if there is a kind of volcano or mountains, or many natural resources. Many natural resources, just based on mixing these, spectral images, you can get so many informations, and it's been proved by the literature, those who are working in the geology and the geographical stuff, and seismology and related to the imagery. They have actually encountered so many applications, just taking different combinations of the spectral images. They can figure out, for example, what kind of resources they can find there. looking at the features, we have, for example, patterns in the images which are really important. When we have the pitch frequency, formant frequencies in the speech, just corresponding to that or equivalent to that, we have patterns as the features of important features of images. So different patterns make sense for different images. We also have colors, we have edges, and these are all representative features out of any image. So if we can have more features, that would actually provide us with a good way of classification of the images or segmentation of the images. For example, we have applications, it's called image segmentation. You have an image, and you want to just to classify or to extract out the pedestrians from those images. People who are walking, for example. Or you want to just segment the animals, for example, dog. Only dog out of the entire image to find out the dogs. Or the cars. Or a specific kind of car. For example, Chevrolet. If you have something as a topic model, if you have something learned already with the system, then you go image segmentation, you go through the image segmentation and you just try to figure out where inside that image you can find this type of car. So the DSP theory has intersections with so many scientific areas, and including, for example, speech, image, or video processing. You can have it can have some intersections. It can have some intersection with communication theory, with computer vision theory, machine learning and optimization, and so on. Yes, please.
The texture is the patterns that we find in the image, right?
Yes. Actually, any pattern that you see here, they have colors.
Yeah.
They have the texture. And they have the edges. The texture is actually a kind of pattern which can be learned, for example, using a neural network. For example, here you have these small circles or the elliptic areas. And in some places, for example, here you have fractals. Fractals are really important nowadays. You know, people, they never cared about the fractals. The fractals, here you can find different types of fractals. If you just learn a single type of fractal, then you can just generalize that fractal for the entire image. These are the fractals. These are, maybe here, for example, the edges is something that works well here, and also here you have some edges also here. But here you have also this, fractals, these small parts here also. Inside every chaos, you can find a kind of regularized and organized pattern. There's not the entire chaos, anywhere. Even inside the entire, there was a lecture in TED Talks. I don't know whether you're familiar with TED Talks. There are so many nice lectures you can find there. There was a professor, one of the founders of the fractal theory, and he was talking about the different types of fractals. He said that 20 years ago, in a kind of research, he started to look at the Brownian motion. The Brownian motion is the most crazy and wild emotion that you can imagine. But even he could find a pattern out of that. And that's crazy, you can just extract out the pattern out of something completely random, at least something that in an initial looking, it looks completely random. So there are so many things that you can learn out of that. Maybe for the human it's really hard to get it, but if you have, for example, a deep neural network with so many inputs and outputs and hidden layers, who knows, maybe that neural network feeding, a bunch of data. When I say a bunch, I mean thousands or tons of data, then probably the neural network will get some information out of that. Or it will learn some kind of pattern or fractal out of that. And then it can easily generalize it for a new test data. Okay, just briefly talking about some of those topics that I explained in the schedule as the outline of the course. let's talk about the multi-sensor signal processing. What I mean by multi-sensor, there are two different very nice applications for multi-sensor voice processing or audio processing, which are called beamforming and blind source separation. So multi-sensors, if you have a kind of noun geometry for the sensor, if the geometry of those sensor arranged, together, if there's a kind of geometry out of that, a pattern out of that, then you will get so many nice advantages. And the theory behind array processing and beamforming is actually developed based on the noun geometries. That geometry should be, for example, it can be just a linear geometry, line, or a circular, or a spherical, or many nice, geometries. You can put the sensors in nice geometries, grab the signals, and then based on the geometry of the sensors, you can come up with some crazy advantages and results out of that it was actually unbelievable in the beginning. So here's a project in the CMU University, Carnegie Mellon University, that they put actually 4 cameras in front and 8 microphones, and they actually gathered both the audio and the visual signal, and combined the audio visual signal, they could easily, even though the window here, the window next to the passenger was actually down, it means that there were a lot of car noise and the environmental noise. But the ASR system, the speech recognizer system, which takes the speech and converts into the text, it could easily actually do that, just using these types of if you just put one microphone here, it's crazy. The result that you get is too much erroneous. But if you just make several sensors, and even you add it with some video signals, some cameras, then the results actually drastically get better. So for the case that we have no geometry, it's just distribution of the sensors. You have multiple sensors without any noun geometry. Then the idea is called blind source separation. You will not get the advantages of that known geometry, but just because you have multiple sensors, it gives you the opportunity to use kind of priors, some prior knowledge, that if you take the feedbacks, here's the process, is the system, the process that, for example, goes for separating the sources. For example, you have 3 people talking in a room, but their voices are actually gathered with different microphones, n number of the microphones, without a known geometry. It's just distributed. If you just get the signal, if you just use one microphone, it's very hard to do to catch the different signals. But if you have multiple sensors, multiple microphones here, then this process, if you take the feedback and here you do a feedback processing using some prior knowledge, prior information, then you can pretty much you can separate these signals with a good quality. So that's the 2 different applications coming out of multi-sensor signal processing just for the voice case. You can have the same thing for the videos, for the images, and so on. Okay, this is also belonging to the microphone array with noun geometry and the beamformer. I don't want to go through the theory now because we have a lot of things in theory later on, coming up later on. Then the idea of pattern recognition or machine learning in signal processing, one of the other topics. So machine learning is, the name brings up the idea with itself. It's learning. So if you can have some training data, you can learn from that data, get the pattern for some features, and then if you get the test data using the model which is already trained by some training information, then you can make a decision for classification, for regression, or whatever. whether that part of the signal which is missing or has been corrupted by the noise should be A or O or whatever. So that's based on the learning idea. Another application should be, for example, musical genre classification. You get a music, and you want the computer to classify whether that belongs to the classical music, country music, rock music, jazz, whatever. So you can just classify the types of the music. Another applications, for example, would be speaker recognition. Most of these applications are just belonging to the speech case and the audio case. You can have tons of applications for other signals. Speaker recognition. Well, you just want to know whether that speaker is a specific person or not. So, 2 years ago, a professor from one of the universities in Costa Rica, he actually came to our lab, and he had a project in his country that they wanted actually to. They had a lot of speech recordings in the court, which was belonging to 20 years ago. They wanted to document those speeches. And for this documentary, they actually needed to know who is actually speaking. They already know the names. They have some samples, but in a court, normally people, there's a variation in the speaker. So, for example, one starts speaking, then in the middle someone cuts, makes interrupting, and then the other one speaks, and so on and so forth. It's really crazy, and nobody can do it manually. So he needed actually, it was a project actually launched in Costa Rica. They wanted to just know the speaker at a time. The project is called speaker diarization. So who speaks when? That's one of the applications. Or speaker identification, who is speaking at one time. Speech security is really prevalent in UK nowadays. Edinburgh University is working on it. So making speech-based locks or speech-based security systems. And you have some processings, the mathematical processings like linear discriminant analysis or PCA, which they try actually to reduce the dimensionality of the data. That makes sense when you have large data. When you have large data, dealing with the large data, large number of the features in the computers is actually time taken, it's very costly, computationally costly. So what they normally do, or the machine learning people do, is that they try to just get those amount of features which are really necessary and informative. If, for example, we have 1,000 features, and among all, just there is 20 features which are representative and the most informative, and they contain 99% of the information, it's so, reasonable to just forget about that 1% to the cost of reducing from 1,000 features to 20 features. So dimensionality reduction, like LDA and PCA, are two types of processes that helps to get that advantage. We have modelings or analysis of the signals and systems both, which, for example, they're called linear predictive coding. For the case that, for example, for the signals which are stationary signals, it means that the statistics of those signals do not change widely by the time. So it means that, for example, the mean and the variance doesn't change too much wildly. They are almost constant over the frames. Then there is a theory, we'll go through that this kind of signal can be very good represented by the linear prediction. And linear prediction is a very simple process and very nice model that can model such kind of signals. And it actually helps to encode the signal. One of the voice coders that were used in the military is called LPC10E. It's just linear prediction for the speech, and they're using in the military transmitting of the signals. So instead of, you know, that the speech signal is actually the voice or the speech is actually between 0 to 8 kilohertz. So the most representative and informative part of that is between 0 to 4,000. Or people say 3,400. Doesn't matter. We just round it to 4,000. It means that for every second, you need to have 8,000 samples. And if you use or assign 8-bit, just 8-bit for every sample, it means that 8,000 times 8 bits for just 1 second. For just 1 second. And for military applications, it's crazy. You have the hand walkie-talkies. You know, the amount of memory that you can put inside the walkie-talkie, at least when I'm talking about 25 years ago, you couldn't find that much memory. So what the people were interested was how to encode, to do the compression of the speech signal, such that, for example, using, instead of, 64,000 bits for 1 second, just using 2,400, how it's possible to get the same quality and the same resolution. So 2.4 kilobits per second. These are the compression ideas in speech case. So it started from LDPCA, PCM, LDP, PCM, then in the mobile handset it started to be RPE, LTP. The first GSM mobiles, they were using this compression RPE, LTP, which was 13 kilobits per second, almost 5 times compressed. And for the military cases, it were going down to 2.4. And nowadays, people are talking about 600 bits per second. Using the algorithms and the mathematics, going to 600 bits instead of 64,000 bits. You can imagine how much compression is that. And it's necessary in the military cases because they are using the HF band, high frequency band, HF band, which is really noisy. It's very good for the long distances. So using a minimum power, you can send the data, the speech data, to 1,000 kilometers away. But at the same time, that has the disadvantage that the environment is so unstable, and together with the noise. That's why they have to, if they have, for example, this part of the frame belonging to the real speech, the informative part of the speech, but they also need to have a lot of redundancy information for the encoding, that when it passes through the channel, which is really noisy, then in a real-time sense they can get the information, and those redundancy information, they are just used in order to get rid of those noises or the errors that might occur for the bits. So if you have 8 bits and one of the bits is lost, there are so many other informations around that those informations help you to get back the information of that bit. So those redundancies are inevitable. You have to use them. And it doesn't matter whether you are working with 64 kilobit per second in the military, in the HF band, or you're using the 600 bit per second, because those, corruption effects will, in any way, they will happen. So it's better to have lower bits in such a way that adding those redundancies, you can have a reasonable frame length, and that frame length is actually happening in real time. So for the military, it was more than 25 years, it was one of the highest topics and the hottest topics happening, speech compression. Okay, for the case of image processing, we have image filtering, for example, linear filter, that you can get rid of some salt and pepper noises. Here you see some salt and pepper noises. Just using a normal Gaussian filtering, you can have the kind of image which you get rid of those salt and pepper noises. And we have so many other even better filters that can keep the quality of the image at the same time getting rid of the noises. One of these enhancement methods we have the same names for the speech and the image. They are called spectral subtraction and Wiener filter for both cases. And I will try for the speech case to show you the spectral subtraction and the Wiener filter. We have the literature. All of these literatures together with all I mentioned, you can use it. This is the one that I mentioned, this Alan Oppenheim from MIT University. That's a large book and it's very, together with many examples. This one is in German, if you're interested in to read some book in German, together with C examples. There are so many C examples inside, but it doesn't cover the theory. I can say just 10% of the theory is covered there. For the machine learning algorithms, the book of David Barber is a very good book, nice book. And also has so many MATLAB files, you can download it from his website. And it's free. The book and the MATLAB codes are free. You can just get it. And for the case of speech, in all different aspects and areas, there's a nice book, Gathering All the Information, Spoken Language Systems, by the Microsoft Research. You can download this book, I think. Otherwise, you can have this book in every library. So let's go through the different types of the signals. We have signals which you can write it down with a formulation. And you can reconstruct the signal just based on the formulation. So knowing one place, the initial place, or one point of that signal, and knowing the mathematical form of the signal, the generation of the signal in the mathematical form, you can easily have the signal by yourself. And you can predict the signal until the far future. These types of signals are called deterministic signals. Everything is determined with these signals. You have, for example, this is a sine or cosine signal. Simply, you can write it down as a sine of omega, and you can easily figure out what's the frequency of the signal. Take 2 peaks in the time and inverse it. That's the frequency of the signal. And depending on you're starting from the 0 or a value, then you can have a shift in the phase. That's all. But we have also random signals. And for the random signals, like the speech signal, and many real signals are random actually, it's unpredictable. You cannot predict the signal. You can just predict some information or some states underlying the signal, but not the signal itself. That's why they're called random. But it depends. Random is just in the limit. So we don't have any kind of signal which is 100% random. You can have some kind of information out of that. And the amount of information you extract out of that in information theory is called entropy. So different entropies means how much randomness that signal contains. The most random signal is the Gaussian signal. So that's the highest ranking of randomness. For such kind of signal, which is Gaussian, the entropy should be the maximum. And when the signal gets farther from the Gaussian distributed, when the random signal gets farther from the Gaussian distributed, then the amount of entropy drastically drops down because it's actually getting far from randomness. It means that there are some kind of predictabilities that are coming up. But as an engineer, we have to know what are the things that you can predict out of that signal. Still, the signal belongs to the random signals, but not that much random as a Gaussian. So, another categorization of the signals are causal signals. Causal signals are, in an analog case, we can just easily say that the only signals which are in real scenarios applicable and really available are the causal signals. So the signals which are causal, it means that before you kick off this device, there's no signal, and when you turn it on, after you turn it on, the signal starts to be generated. That's a normal, the most intuitive definition of the causal signal. Now we have signals are called anti-causal. It means that the signal has already been generated until you turn it on, and then it stops being generated, which is by definition far from the intuition and the mind. And non-causal, it means that it has in both sides, so before and after. Intuitively speaking, the causality means that the signal at any moment depends on that moment, condition of that moment, and the previous memory of the signal, but not in the future. So signal which is generated at time n only depends on the input at time n and the previous values of the signal at time n minus 1, minus 2, minus 3, and so on, but not depending to the future of the signal. And that's why non-causal signals or systems are not implementable. How is possible that the signal at the moment depends on something in the future? Future is not coming, so we don't know about the future. That's why it's implementable. It's not implementable, but when it's causal, because it depends on the past, so you can have the signal from the past, and then you can use it to create a signal in the current time. So causal systems are implementable, but not the other way around. So that's the definition of causality. Another categorization or classification of the signals is discrete versus digitized. When we have analog signal like the left-hand side, x of t in the left-hand side, that's kind of analog signal. Then if you take the samples exactly in the amplitude of the analog one, it's not digitized, it's just discretized. So we have discrete time signals and we have digitized signal, which are two different concepts. So the right-hand side is just a discrete form of the left-hand side, but not digitized. The meaning of digitization comes together with quantization. So if you see the lower figure, the left-hand side is a continuous time and continuous value signal. Then you take the samples, and if you just take simply the samples, you will get the right-hand side, which is continuous time. Well, here, sorry, the bottom of that analog one, you will have the discrete time and the continuous values. So it's kind of sample and hold. It takes the sample at the instant time, but it's holding the value for a while until it takes another sample and holds the value, then the next sample holds the value, and so on. But this is not something that happens in reality for the A to Ds. A to D converters, what they do is actually they put different quantization levels and they assign the value of the signal to the closest level of quantization. So if the signal, for example, in the first sample is closer to this level, then this level of bits is actually assigned to the amplitude. And the closest level is actually assigned to the point that you take the sample. I will show you in more detail in the next slides. So after doing the quantization, that's called the digital signal. Beforehand, it's just a discrete time signal. That's all. As an example of quantized signal, if you have an input like that, sinusoidal or cosine signal, for example, if you assign 3 bits, using 3 bits, you will have 2 to the power of 3 different levels. Is that okay? So it means 8 levels. The maximum number of the levels is 8 levels. So the signal should be quantized between these 8 levels. Any of these levels which is closer to that sample that you take, that sample is actually put inside. For example, if you have this signal and then you take the sample, let me start the signal from here. If I take that, I put a DC for the signal, put it here, and then I start digitization from this level. And I put it 8 levels. It means 3 bits. Then if you take the sample here, taking the sample here, then so you will get, for example, 0, 0, 0. And it means the sample is here. But if you take the next sample, for example, here, and you get this value, then it looks at the closest level, which is this one, and then what it puts here is, for example, this value, 0, 1, 0. And for any samples that it take here or here, because the closest level is here, it just puts, and for the negative values, we have this bit 1. For the positive values, this bit is 0. For the negative, is just 1. So all of these samples here, they are actually cramped, and they are just getting the value of 0, 1, and 1. And it doesn't matter whether this analog value is different from this one or this one. Doesn't matter. This is how it's shown in this figure, the quantized level. So when you have 3 bits for the digitization, you have the resolution of the signal like this. When you have 4 bits, you have like this. And the number of the bits increasing, you see that the signal in the output gets more closer to the signal in the input. So we have also the binary signal. We have a multi-level signal. So binary is just including 0 and 1. Other than this 0 and 1, you can also have multi-level signals, like 0, 1, 2, 3, and so on. And that normally happens in telecommunication, like HTTP3, for example, coding. They use it for different levels because it's more noise robust. In general, an A to D converter, analog to digital converter, and the contrasting process, something that happens like this. So you have the analog signal on the right-hand side. You have an analog signal, you sample out of that. Then you digitize and quantize it, actually, and digitize the signal. And then you do the reverse process to get the analog signal. But the point is that if the quantization level is not large enough, then what you get in the output has some errors compared to one in the input. Even if you do any process, there would be some error existing in this process. From the beginning to the end, there would be some error. And that error is called the quantization error. So starting from the process, even if we have done nothing, we have a kind of error which is unavoidable. And that error is called quantization error. It's unavoidable. Yes?
That is because of the sampling rate.
Because of the sampling, because of the digitization level, both. So these two pre-processings are actually very critical. And that's why at least 20 years ago, one part of every task that the engineers in the signal processing should know about that was to define the dynamic range of the signal and to actually determine what kind of A to D converter is necessary and how to cope with those quantization and digitization levels and the frequency, sampling frequencies. Because the A to Ds, evolving the time, the A to D converters are, improved a lot. Maybe nowadays we don't have to care about the A to D converter. The A to D converter is actually developed just, simultaneously with the types of the signal and applications related to that. But back to the 30 years ago, we had images with the minimum bandwidths of 2 megabytes, but we didn't have such kind of A to D converters for that. So we knew already, at that time, that there is a kind of limitation, and that's the limitation that we know already, that the quantization error is existing. How can we can make a process, to get better results out of that? For the multi-resolution, in that outline you saw about the multi-resolution, that's the wavelet. If you go just to the MATLAB and write the wave demo, you will get, for example, that's a GUI program, the graphical user interface. You can just open an image, like the Lena image. That's a very famous picture for the test in the image processing. It's called a Lena. You give the image, and it actually uses the multi-resolution analysis. It's a wavelet, the first wavelet, the Haar wavelet, for example. You see there's in the top corner, top left corner, that's the compressed version of this. And the rest are actually the details. They are the details. And you can, based on your need and your requirement of the process, you can actually ignore from some level the detail, level of details onward. You can ignore it. And that means compression. Definitely the quality of the original picture is higher, but maybe for your eyes, still, you have the quality that you need. So that's the multi-resolution analysis in the wavelet domain. So that was the first lecture. In the afternoon, we'll go through the next one, which is mostly processes, Fourier domain, and sampling theory, and so on. Any questions so far, or any ideas? I'm very happy to take your comments, questions. And if you don't, we can just meet each other at 1:30. Thank you. Anybody has any kind of solution how to... There are some things that I want to actually... I'm recording. You see that I'm recording the screen. So I just want to have the recording of the screen, and maybe I'll put it in the YouTube, maybe replacing with the previous ones. I'm not sure. But I don't want to write down things on the blackboard, because if I can write it down on the tablet, and then the tablet is somehow mirrored on my laptop screen, then automatically it's actually recorded. And I can easily write down on this, just like I'm writing on the blackboard. And all the things will be recorded at the same time. So if you have any solution for that, I know that there's a software called Mirror Up, but it didn't work for my laptop and for my tablet actually. If you have any other solutions, I'll be so happy to get your advice for the next time, maybe.
Just one question.
Yes, sir.
So I already have admission for exam, but I want to do homeworks maybe for me. But if I commit those homeworks, can I lose my admission if
No,
if I
yes,
don't do
sure.
them well?
No. If you have already got the admission for the exam from the last summer semester, you don't need actually to give the exam again. You don't need to actually to give me the homework, the solutions.
Okay.
You can just take it for yourself, and you don't need actually to send me anything. Just participate in the exam.
Okay. But I can participate in the project to get this extra point for.
Sure. Yes.
Okay.
Yes. The project is quite different. You can participate in it, and I can get a point for your exam, because it's just for your exam. But for the homeworks, you don't need to give anything. But if you want to do it by yourself, it's a point of advantage for yourself.
Okay. Because I wrote you this email. I listened to this course in 2014 with
Okay.
Professor Glacker.